Welcome to QOD number 53. Can't say how many more there'll be. It depends on how energetic I am in the next few days. But we shall see if there are going to be one or two more. Anyway, we've talked, so we're in chapter 13. We already talked about solubility as it relates to intermolecular forces, sort of qualitatively, in terms of like dissolves like, et cetera. And we've done an experiment on that. This is more nuts and bolts types of terminology and energy around formations of solutions. So here's a picture of a sodium chloride, a depiction of a sodium chloride crystal dissolving in water. And just to remind ourselves of some of the terminology, a solution is a homogeneous mixture in which you've got two or more substances. The thing that is there in the greatest amount is called the solvent, and the thing that is there, the substance or substances that are there in lesser amounts, are known as solutes. We can have three different types of solutions. The image that most of this chapter is kind of, or the first part of this chapter has to do with dissolving ionic things in water, and sodium chloride is kind of the sort of the standard for that. We will talk about other types of solutions as well, not just aqueous solutions of ionic compounds. But we can really think about three different types of solutions. You could have a saturated solution, an unsaturated solution, and a supersaturated solution. So in a saturated solution, really that really means that you've got the maximum amount of solute dissolved in that solvent that can exist in equilibrium with undissolved solute. So in other words, you really know you've got a saturated solution when you have some undissolved solute in the bottom of that and it can't dissolve anymore. So for example, in a laboratory, when I was working in a laboratory and I wanted to have a saturated solution of sodium chloride, I would get some water and I would put so much sodium chloride into it that no more would dissolve, and then a bunch would lie on the bottom. And therefore, you know you've got a saturated solution because you've got the maximum amount of sodium chloride in solution that can exist in equilibrium with undissolved solute. Most solutions are unsaturated. If you think about the various solutions that we've used in class this year, you know, for example, a solution of an acid or something like that, we could typically always have made that more concentrated. If you think about drinks, sodas, Gatorade, things like that, they could be made more concentrated. It's very rarely the case that you encounter a solution in life that is a saturated solution. Most of them are unsaturated, which means that there's less material in there less solute in there than could possibly be at a given temperature. You can also have a supersaturated solution, and that's when you have more solute in solution than a saturated solution. How's that possible? That's because at that moment it's not in equilibrium with undissolved solute. It's very unstable. And so the image you have here is a supersaturated solution of sodium acetate. And if you drop just a tiny little piece of solid sodium acetate in there to act as a seed crystal, you'll immediately get this huge crystallization event until it equilibrates at a saturated solution, in which you now have a saturated solution in equilibrium with undissolved solute. I'm sorry. This happens fairly frequently in organic chemistry, that you get things that will crystallize if you scratch the side of the flask or put a seed crystal in. They're rare, they're unstable, and so you really wouldn't normally encounter a supersaturated solution in your daily life. So how does the solution form? Well, it's simply, in the case of an ionic substance in water, the ions are essentially just going to start diffusing away from the crystal and solvating. And the term solvating really means that those ions are being surrounded by water molecules. In other words, being surrounded by solvent molecules. So here water is the solvent. You can see that these water molecules are surrounding a hydrated chloride ion or a hydrated sodium ion and solvating them. In order for that to occur, in order for a solution process to occur, and we've touched on this in the lab and some of the conversations we've had already about solubility, the intermolecular forces between the solute and the solvent have to be similar to the intermolecular forces between solvent particles and between solute particles. So in the case of dissolving sodium chloride in water, it's necessary that these ion dipole interactions between water and sodium ions, or water or chloride ions, have to be fairly similar in magnitude to the lattice energy of the sodium chloride, which is what's holding a solid sample of sodium chloride together, and the hydrogen bonding that is sort of holding the water molecules to each other in liquid water. And so for an ionic salt to be soluble in water, it's going to be because those ion dipole interactions that you are creating here as you are solvating, hydrating those ions, those ion dipole interactions need to be very similar in magnitude to the lattice energy of your crystal, and also to displace the hydrogen bonding between water molecules as they're floating around in solution. This doesn't necessarily only apply, obviously, to aqueous solutions. As we've said before, here's an example of chloroform and acetone, which are two organic solvents. Neither of them can hydrogen bond, but they are both polar. Acetone is more polar than chloroform, but they both have a permanent dipole, and therefore they are going to interact by dipole-dipole interactions. And acetone and chloroform are miscible in each other. That is, they are freely soluble in each other in all proportions. And this is just another example of what we described before, that when it comes to solubility, it's generally the case that like dissolves like. Well, let's talk about energy changes. What makes a solution process exothermic? What would make a solution process endothermic? And then whether or not a solution process would be spontaneous. In terms of delta H, that is heat that goes into this, you really have three things. There is a delta H of separating. So here's what you've got: pure solvent, you've got pure solute. You're going to make a mixture of them. In order for that to occur, three things have to happen. You have to spread solvent particles apart from each other, which means breaking the intermolecular forces in the solvent. You've got to put energy into pushing solute particles apart from each other, which means breaking the intermolecular forces, or the lattice energy, if it's an ionic solid, of whatever that solute is. And then there is energy that comes back by the intermolecular forces between solute particles and solvent particles. And this is going to be very similar to what we talked about back in chapter 8 when it came to bond dissociation energies. You put energy into breaking bonds, you get energy out of making bonds. Similarly here, you are going to have to put energy into breaking intermolecular forces. You're going to get energy out of creating new intermolecular forces. And so this light blue arrow represents the sum of the dark blue arrow and the green arrow. That is the total amount of energy required to push the solvent particles apart, to push the solute particles apart. That's the total energy expended. And then this red is going to represent the energy that you get back, the energy that is released when intermolecular forces are created between solvent and solute particles. And if if this red arrow if delta H for the red, the third step, is more negative than the sum of the first two steps, then you'll have an exothermic process. In other words, you got in an exothermic process, it's because you got more energy out of forming intermolecular forces between solvent and solute particles than you had to put into pushing apart solvent particles or pushing apart solute particles. If this red arrow is greater in magnitude than this blue arrow that represents the sum of these two, then you'll have an exothermic process. If, on the other hand, you have to put more energy into the sum of breaking apart solvent and solute particles than you get out of forming the solution. If you have to put more enthalpy into that, if this light blue arrow is larger in magnitude than this red arrow, then that's going to be an endothermic process, and that process will absorb heat. Well, we know in general exothermic processes favor spontaneity, and so you would tend to think that if something was going to be soluble, it would tend to be an exothermic process. But we know, in fact, that there are a lot of endothermic solution processes that are spontaneous. And one very well-known example is cold packs. A cold pack comes from dissolve. So what you have in a cold pack is you've got a little bit of water and a big chunk of solid ammonium nitrate. And when you break it, what you're actually doing is breaking a membrane that allows the two things to mix. As the ammonium nitrate dissolves in water, that's an extremely endothermic process. The temperature goes way down, and you have this this cold pack. And ammonium nitrate is tremendously soluble in water, and yet it's an endothermic process. And so we want to go back and think based on what we talked about with thermodynamics in chapter 19 about how that can be. Remember, spontaneity of a reaction or a process does not simply involve delta H, it also involves entropy. And it's pretty much always the case, and I'm going to mention one case in a minute in which it's not so, but in the vast majority of solution processes, there's an increase in the entropy of the system. And remember, entropy just means a disorder or randomness or available microstates. And if you think about a separated solution, say just glass of water and a chunk of sodium chloride, they are more highly ordered when they are separate from each other than when they are mixed with each other. There are generally more microstates available in this solution than there are in the more highly ordered, say, solid ionic compound and a container of water. And so most solution processes are accompanied by an increase in entropy, that is, an increase in delta S. Well, you'll remember that delta G, it's delta G, the free energy, that determines whether or not a process is spontaneous. That is a combination of delta H minus T delta S. And so if you have a solution process for which delta S is sufficiently large, that is, you have a really big increase in entropy as you are mixing these two things, then that can be large enough to make delta G negative. Remember, a negative delta G uh, is what you need for a spontaneous process, even if delta H is positive, which is an endothermic process. So if it's endothermic, delta H is going to be positive. But if delta S is large enough, then you can still have a negative delta G for that process. And so that's certainly the case when you are dissolving ammonium nitrate in water. It's clearly an endothermic process. Delta H is actually fairly large and positive, but the delta S must be quite positive in order to make delta G negative, which it must be, because as I said, ammonium nitrate is very soluble in water. It is possible to have a negative delta S for a solution process, and that may seem a little bit counterintuitive because, as I said before, you have a fairly highly ordered glass of water, you have a fairly highly ordered salt crystal, and so when you mix them together, isn't it always going to be the case when you're dissolving one thing in another thing that you've got more microstates available? Well, that's certainly true with regard to the solute. But if you look at these, if you look at this image and they show a couple of these purple ones are sodium ions, and you can see particularly that there are a lot of water molecules clustered around those sodium ions. For some cations, particularly cations like mercury and lead and silver, you get not just one shell of water around those cations, but you can actually, and I was looking, hoping to find an image of this online and never did. You can get 2 or 3 actually shells of water around them. They're so highly charged that they make the water around them so ordered that you get actually a fairly large decrease in the entropy of the water because you get these almost little ice crystals forming around cations. And so it is possible for some, particularly in the case of some highly charged cations, like aluminum and lead and mercury and other examples, to have such an ordered state of water around them that the total entropy of the system actually decreases. But that tends to be an exception. The norm tends to be that when you mix things together, you get an increase in overall entropy of the system. Let's talk just for a little bit about the solubility of gases. And we know that gases are soluble in water. We know, for example, fish breathe because oxygen is soluble in water, and it's sufficiently soluble that fish never need to come to the surface. They can simply take oxygen that is dissolved in water in through their gills. We know that carbon dioxide is soluble in water. That's the basis for carbonating beverages. And so gases are soluble in water because they tend to be, because a lot of gases tend to be nonpolar. Solubility tends to be a function of size. And so the larger a thing is, a krypton atom is bigger than an argon atom. Argon atom is bigger than an oxygen molecule. Oxygen molecule is bigger than a nitrogen molecule. Carbon monoxide, because it's polar, you're going to get some dipole-dipole interactions with water, so that kind of increases its solubility relative to nitrogen. But in general, if you just look at the nonpolar ones, nitrogen, oxygen, argon, krypton, you'll see that they get more soluble in water as they get larger, and that has to do with dispersion forces. The other big important thing about solubility of gases has to do with the partial pressure of the gas above the solution. And so here's a great, I always love graphs that give more than one bit of information. So this is giving you a couple things. It is showing you once more that oxygen is more soluble in water than carbon monoxide more soluble than nitrogen more soluble than helium. But the other thing it is showing you is that as you increase the partial pressure of a particular gas above the solution of the gas in water, that substance becomes more water soluble. And it's a linear relationship. If, in other words, oxygen is twice as soluble in water at 1 atmosphere of oxygen above the solution than it is at 0.5 atmospheres of oxygen above the solution. So that's a direct proportion. And that makes sense if you think about this in the context of Le Chatelier's principle that we talked about earlier in the year. If you think about dissolving, say, carbon dioxide in a soda in water, you can just think about an equilibrium like this. And if I increase the partial pressure of the reactant, that is going to shift the reactant toward products. That's going to increase the solubility, the concentration of carbon dioxide in water. So this makes perfect sense that there ought to be a fixed direct relationship here if you think about this in terms of Le Chatelier's principle. And we can express this in terms of what's called Henry's law. And Henry's law simply means the solubility of a gas, that is the concentration of the gas in solution, is equal to what's called a Henry's law constant, which is specific to the particular gas and solvent at a particular pressure. So in that sense, it really just is an equilibrium constant. That Henry's law constant times the partial pressure of the gas above the solution. So as the partial pressure of the gas goes up, the solubility of the gas is going to go up. This is a direct proportion. As the partial pressure of the gas goes down, the solubility of the gas goes down. So right before this person uncorked the bottle here, the solubility of carbon dioxide was greater in the solution because the pressure of carbon dioxide above the solution was greater. As soon as you crack that lid open and carbon dioxide can escape, that partial pressure decreases. Therefore, the solubility of the carbon dioxide decreases and it starts to bubble out of solution. And you saw this in a Le Chatelier's principle experiment that we did in a lab this year with syringes and seltzer water. So here's a typical problem you could get for Henry's law. So here we go. This is, by the way, the only animated slide in this particular presentation. But the concentration of carbon dioxide in a soft drink bottled with a partial pressure of carbon dioxide of 6.5 atmospheres at a temperature of 29 degrees Celsius is 2.2 times 10 to the minus 1 molar, or 0.22 molar. Calculate the Henry's law constant for carbon dioxide at this temperature. Well, we just said that the solubility of a gas, which would be the concentration of CO2 at equilibrium, is equal to the Henry's law constant times the partial pressure of that gas. We can rearrange that, and again, now you can see that this is really just an equilibrium constant, because this is concentration of over products over concentration of reactants for the solubility equilibrium. And so S and P are actually given to us. The solubility is given as 0.22 molar. The pressure is given to us as 6.5 atmospheres. Therefore, we can evaluate that. That comes out to 0.034 moles per liter per atmosphere. And that would be 3.4 times 10 to the minus 2 moles per liter per atmosphere. So there's a typical problem you can see on Henry's law. Just real quickly, when it comes to the temperature and the solubility of things, this is a list of ionic compounds and their solubility in water as a function of temperature. And what you can see is there's no correlation at all. It really, some things are much, much more soluble in water at higher temperatures. And you can see this is particularly true of nitrates. Some things actually, cerium 3 sulfate here, becomes less soluble in water at higher temperatures. There's more than one compound that does this. It tends to be an exception, but you can certainly find compounds that are less soluble at higher temperature. Sodium chloride, which is probably the most common thing that we might dissolve in water in our daily lives, actually the solubility varies very, very little with temperature. Between the freezing point of water and the boiling point of water, the solubility only seems to go up about 5 or 6% here. So, so there's no real correlation here, but it's generally the case that it increases with temperature. It is always the case with a gas, dissolving a gas in water, that it becomes less soluble as temperature increases. This is something that we kind of know from everyday life. Say a soda gets more flat as it warms up. And it's going to get flat faster as it warms up. If you've opened a soda and you don't want it to get flat right away, you put it in the refrigerator rather than leaving it out on the countertop. That's because gas has become less soluble in water or in any other solvent, but I think here water is the solvent, as temperature increases. And you can see that this is a well-behaved, well-defined relationship, and this is directly related actually to what we talked about in the past about vapor pressure. As temperature increases, vapor pressure increases. And if you have a mixture, the thing whose vapor pressure is going to increase most quickly is going to be the thing that is most volatile, that is the gas that's dissolved. So it's going to come out of solution fairly quickly as you increase the temperature. Okay, I think that's everything I have to say. And so there will be a QOD the next time we meet for class. And so thanks for watching.